Let's go ahead and get started.
You don't have
First of all, it's a pleasure to introduce Professor Michael Lisa. I've known him for longer than Helen knew him, has known him.
Ongoing, we don't put it in the past tense yet here.
Anyway, so Mike got his PhD from Michigan State University, and I was going to mention he was at Notre Dame as an undergrad when Sierra was here, but I know where Sierra went.
I think.
Are we getting feedback?
Yes, we're getting an echo. Is someone not muted that is in?
Should be muted.
Or has
Sign it right, I
there,
guess.
yeah, I guess volume up.
How's this?
A
Still,
little
How do
bit.
you know?
I just
Yeah.
heard
Okay,
like.
probably that was me, maybe try.
How about now?
Yeah.
That's better.
All right, so welcome. Seat and again, let me start over. Professor Michael Lisa from Ohio State University. It's been a pleasure knowing him for a long time. He got his PhD from Michigan State University, then was hired actually into our group at Berkeley as a postdoc, as a fresh postdoc. And then immediately after 3 years as a postdoc, joined the faculty at Ohio State University. I think that was quite an accomplishment. Mike, since I've known him fairly well, is quite creative, and he does different types of analyses and different experiments and even other experiments, you know, like in astronomy now. He is an APS fellow and AAAS fellow, and I think most recently a University Distinguished Scholar.
Professor now also.
Professor, right. You were a scholar until last year. Okay. Of which there are only, I don't know, 20 or so at Ohio State University. So anyway, you see what Mike's going to talk about, both nuclear and some of his, let's call it astro intensity, interferometry interests, and other interests in STAR that he's been involved in. Please, Mike.
Yeah, well, thanks. Thanks, John. Thanks for the invitation. It's a pleasure to be here. So yeah, I'll be talking about intensity interferometry from the stars to STAR and back. This is a reference, of course, to many of us who work in STAR, the nuclear experiment. And I'll focus on measurements of gamma Cassiopeia by the VERITAS collaboration. My talk comes in 3 parts. I'll start off with a description of the technique of intensity interferometry, which I think is not necessarily well known, as well as some of the history behind it, because I find it actually quite fascinating. And it's important for understanding some of the questions that are brought up in terms of quantum mechanics. I'll spend a little bit of time on intensity interferometry in the subatomic realm with the start of the so-called GGLP effect in 1960, and then femtoscopy as it's still in use today. And I'll describe this a little bit. And then at the end, using technology developed in particle and nuclear physics, there's been a revival of intensity interferometry for stars, and I'll come back to this at the end and then summarize. So if I think about physicists in World War II, naturally many people, especially Americans, might think of Richard Feynman, a brilliant student in classes who was taken out of his degree program, put into a government-run top secret project for the war effort. And of course, we know how this turned out very well, at least for us. In Britain, there was a similar group of people, and one of them is Robert Hanbury Brown. So he was also in school, a brilliant student studying electrical engineering with plans to get a PhD. This was interrupted by the war forever, actually. He never got a PhD in physics or engineering or anything else, even though he became chair of the physics department. He was also drafted into a top secret government-run program for the war effort, but it was much more urgent in the case of Britain because they had to develop radar. They were under attack, whereas things were a little different here. So let me describe a little bit about that. The situation at the time was the German bombers were flying over the English Channel largely undetected and being able to attack at will English cities, which were largely undefended. And there was no early warning system. There was no real serious ground-to-air defense. Britain was under attack and had to develop a program now. That's what they did. The tools that they had at hand were largely these dirigibles here with some kind of cables between them. The idea was that this would get tangled up in the airplanes or so. Didn't work out that well, really. They had a network of spotters on the top of tall buildings, which could give some kind of warning below, really just looking through binoculars at the sky. And I've actually always wanted to visit these sound concentrators, or so-called acoustic mirrors on the coastline in Britain, which are generally either parabolic or spherical shells of concrete with a microphone in the center and cables running to somebody with headphones on to hear the roar of the planes coming over the channel as early warning. Hanbury Brown's story, I mean, he was a pioneer in
I know. I didn't even mean to do it. I can just do it. I'm here.
in the development of
No
radar.
problem.
The host can mute them.
Oh, yeah, very good. He developed early warning systems for the bombers coming across. Very soon afterwards, he and his team developed ground-to-air targeting to defend the cities, and eventually actually air-to-ground as the English started to bomb Germany. He actually lost hearing in one of his ears because he was in the belly of a bomber with an oscilloscope and antennas on the outside. And he has very nice pictures in his book of, you know, finding open country. They were bombing at night and, you know, they couldn't tell where the bombs were going to go, where he would pick up radar echoes of infrastructure that they would like to strike. And even towards the end of the war, they started putting antennas on the wings of planes for air-to-air combat. Okay. So this is the sort of thing he worked on, and it was an emergent, rushed secret project. After the war, you had a bunch of engineers, very bright, highly trained in an area that was brand new, developed covertly and hurriedly, not well organized. So if you read the literature afterwards, at least I find it rather confusing and arcane. Okay, at least for maybe a decade or so. Nevertheless, they had a lot to offer. They were highly trained in a new technology, very creative, and many of them went to science, including Hanbury Brown. In particular, having developed radar, they turned to the new field of radio astronomy. In this case, there were so-called radio stars of unknown origin and unknown structure. Turns out most of them were galaxies rather than stars, but they were measured with Michelson or amplitude interferometry, the type that we're familiar with. And even though we're familiar with it, let me just go through some of the basics. Don't worry, I'm not insulting Yale students here, because I want to make a point. With Michelson interferometry, it's largely along the lines of the two-slit experiment. I can imagine a very far away point source. So I'm thinking about plane waves hitting like two slits, two mirrors, two telescopes, two whatever it is. And then forming on a far screen or photo sensor fringes, dark and bright fringes. So this should be really the intensity. We know about these fringes. We know where the locations will be. It's given by the ratio of the wavelength, which we choose with a filter, and the baseline, the separation between the telescopes or the slits. So this is well determined. One doesn't really learn anything from this. If I have my source not directly overhead, but at some angle eta, I get exactly the same pattern, but it's just shifted by an additive constant. Okay. The point is, stars are generally not point sources. We'd like to measure their size. So it's actually a distribution. And I can even consider, just for simplicity, a point source high up and another point source high up at a different angle. This is sort of a proxy for the opening angle of a star, the angular size of a star. And we can consider what will happen. These 2 point sources and all the point sources on a star are incoherent emitters. Okay, what that means is that these wavelengths are the same. I just colored them green and red to keep track. What that means is the fringe pattern in intensity for the green is shifted over relative to the red intensity pattern. And because they're chaotic, non-correlated, the intensities add. Okay, so what I end up with at the end is a sum of these two. It has not very strong fringes anymore because one of them was shifted over. And just mathematically, one can find there's an oscillatory term, indeed, as before, but there's a multiplicative prefactor, the so-called visibility. And this is what's used by amplitude interferometry, Michelson interferometry, for example, Shara or so, is to measure the visibility. How strong are the fringes? Not where are they? Where are they kind of tells you where in the sky the star is, and typically you're pointing at it. But how strong the visibility is, and it depends on eta, the extent of the star. and on the baseline, how far apart your telescopes are. So by moving the baseline back and forth and watching the visibility come in and out of focus, you can measure the star. And that's the way Michelson interferometries work. Naturally, it's not 2-point sources you integrate over the star, but this makes it simple to talk about. So generally what one's talking about is for a given separation between the telescopes, the difference in the intensities, let's say maximum minus minimum divided by the average, and the resolution of the size of the star you can measure is given simply by the ratio of the wavelength divided by the separation between the telescopes or slits or whatever. Now, there are two problems with that. The main one is that light must, for this to work, light must travel undisturbed from the source to the detectors, slits, mirrors, cameras, whatever that is. Furthermore, you have to recombine the light. So if I have telescopes separated by 500 meters, I have to combine the light onto a common screen while not disturbing the phase of the light. That's highly non-trivial. Nevertheless, it can be done in certain circumstances. The challenges are atmospheric turbulence. That's one of the worst challenges. In particular, this is just a calculation of turbulence in the atmosphere. It's a good model that's called Kolmogorov turbulence. The contours show where the wavelength of light passing through the atmosphere would shift by a half a wavelength, where the wave would shift by half a wavelength. You shift by half a wavelength, the entire pattern is destroyed. Okay, so you can imagine, and these are on the scale of meters here, I have one telescope where there's a certain amount of turbulence over it. Over here, there's no turbulence. Well, this is going to shift the pattern and I'll destroy my fringes. Okay, so I won't be able to measure the star if I have a lot of this turbulence. And this is really a problem at visible wavelengths, as I'll mention. Another thing is one really has to have, if you want to measure small stars, big stars are pretty easy after all, but if you want to measure small stars, you want to have small wavelengths, visible is better than infrared or radio, and large baselines, very far separated. And again, transporting the light, preserving phase coherence and integrity over long distances through fibers or something is very difficult. Nevertheless, this was done before the war by Michelson, who developed Michelson interferometry. He measured the size of Betelgeuse, a rather bright star. He did this with visible wavelengths, green light, using the 100-inch telescope at Mount Wilson. So this is a picture of the 100-inch telescope. I told you what the resolution of a given instrument was. In order to measure, what happened here? In order to measure a star of 5 milliarc seconds, you can go through the calculation and find that you actually need 10 feet, which is larger than 100 inches. I love to give this talk in Europe. So I say listen, that's what was in the literature. It talked about inches and feet, so that's what we're sticking with. So the 100-inch telescope was not enough. What they did is, in fact, bolted a 20-foot Michelson interferometer onto the top. Okay, so they just used the cage only. They didn't even use the telescope. They have mirrors, which can be separated. They were controlled by, honestly, I don't know what they were controlled by, but anyway, they could be separated. And the idea is the light comes down from the top, hits the mirrors, and then is eventually recombined at a screen later. All this through air, so it was preserving the phase integrity of the light. Down at the bottom somewhere, this is an observer. In fact, this is Michelson himself looking through an eyepiece at the fringes, measuring Betelgeuse. One thing he said in his paper from 1921 is that the resulting interference fringes that he was looking at with his eyes, though in motion due to the turbulence, are quite distinct unless the period of the disturbances is too rapid for the eye to follow. So it was a difficult measurement, probably not something that could be easily repeated, and it can only be done on some nights with close by mirrors where maybe the turbulence was similar over both mirrors. You get them further apart and it didn't work. In fact, inspired by being able to measure at least a couple stars with this interferometer, they tried a 50-foot interferometer to measure even smaller, more interesting stars. But this failed for two reasons. One is one had to maintain phase stability within one wavelength. So if you're taking a look at 500 nanometer light, that means your mirrors have to be separated by a distance, and you got to know what it is, and it has to be stable to 500 nanometers, which was difficult with the steel beams they were using. More important, however, was the turbulence effects in the atmosphere. This became impossible, and basically that was the end of visible spectrum Michelson interferometry of stars. Now, the turbulence for visible light is quite bad, but for radio waves, which have longer wavelengths and are more transparent to the atmosphere is more transparent to them, it's much less of an issue. So when our radar engineers came out of the war, they were able, in fact, to relatively quickly use the ideas of Michelson at these longer wavelengths. So this is like 1.5 meters or so, and measure Cassiopeia A and Cygnus A, which were considered stars. We now know them to be galaxies. They're large. They're about 5 arc minutes, which in units that I'll come to later is about 300,000 milliarc seconds. You'll see why I mentioned that later on. And you can see shortly after the war, 1952, 3 simultaneous coordinated publications in Nature, one right after the other. They're all measuring the same source, but observations at different observatories. 2 of them use Michelson interferometry, these bottom 2 here, and they found, well, 5 arc minutes. With the baseline, they had to separate by about a half a kilometer. Okay, so that was a relatively large baseline. This third one by Hambray-Brown used a different device and a different principle. And I like to look back in the literature because I find it fascinating. His paper is only 3 pages long in Philosophical Magazine. And let me just say something about this. This is pretty much the only figure. It's not actually the only figure, but it's the only relevant one. A sketch of the instrument. You can't really tell much from it at all. What he said was, in order to build an instrument that would work at large baseline, for this reason, an interferometer of completely new design and completely different operating principle was designed, okay? Furthermore, the theory of this instrument is very involved and will be given in detail elsewhere. And this got accepted for publication. I mean, I could just say, oh yeah, I did a new thing and I'll tell you later how it worked. Here's the results. I mean, I don't know, but it seemed to work probably because he agreed with the other ones. So this is what there was. And this explanation that I will give you later came 2 years later in a classic paper, 1954. This is the abstract. This is a brilliant paper. But one thing he points out here is it should be possible to operate the new instrument with long baselines and unaffected by atmospheric turbulence. This is a crucial point, that this technique, which I'll tell you about, is robust against these atmospheric effects. And let's talk about why. This is an interferometer that was built by Hambray-Brown at optical wavelengths. We'll talk about optical later. We'll just pretend it's radio. If I have electromagnetic emission from the star coming down here, what Hambray-Brown realized and proved, I won't do it now, it's rather complicated, it really is that if I select a narrow bandwidth, I decide to take a look at a frequency with a very small range, then the intensity of the light fluctuates. So it's happening at random, but there are regions that are bright, 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 dark, dark, dark. It's not periodic or anything, even though this simulation makes it look somewhat periodic. But there's characteristic scales. So if I put my telescopes here and here, they're close together. Pretty much when the blue telescope sees a bright amount of light, then the red one will too. If I now separate the red one, well, there's less of a correlation. Sometimes they'll see bright and dark together, but sometimes not. The intensity correlation goes down. Naturally, I come further apart, and by now there's almost no correlation between the blue telescope and the red telescope. Now, naturally, light comes, well, at the speed of light. These fluctuations are very fast. Depending on your bandwidth, they could be at the femtosecond or even much less time in terms of the fluctuation time scales. Very hard to measure is kind of what I'm trying to say. What he found out is if you use even a more tightly controlled bandwidth, which should go there sometime. Okay, let's see if that's gonna, I don't want that yet. Okay, you should go now. Okay, let's go back to this. Okay, if I use even a more narrow wavelength filter, really select a very small range of lambda, then what I find is the temporal extent of these fluctuations gets a lot larger. That's important because if I want to measure the intensity at a given photomultiplier tube, getting brighter, darker, at let's say the picosecond scale, I want this stretched out. Okay? The point being, it's on my screen. The point being that the transverse extent of the source does not depend on the bandwidth of your filter. It depends on the wavelength you're looking at and the size of the star. That's what you're trying to measure. Okay, so that was true for this bandwidth and also the one on the previous page. The temporal extent, how long does a dark patch last? How long does a bright patch last? The scale of it is set by 1 over the bandwidth. So you'd like a narrow bandwidth so you have a chance to catch these damn things because they happen fast. And you'd like to put your telescopes over the transverse extent and watch the correlation go away. That's the point of intensity interferometry for stars. Okay. He then took the signals from his telescopes. These are optical, but it could as well be radio. Connected them basically by a BNC cable to a correlator circuit of his own design and was able to measure the correlation. And by this method, he could actually, this was a paper shortly after 1953 measuring, I don't remember what star this is, but this is the correlation, the intensity correlation as a function of the spacing between the telescopes. And it's very well described by theory. All this is a Bessel function. This is what you expect for roughly a uniformly illuminated disk in the sky. So he could extract the size of this thing very well by intensity interferometry. Okay. Good. Well, this worked. It was, I would say, even applauded. It was seen as a very nice device. But in this 1954 paper, and the final paragraph, kind of as an afterthought, he said, you know, we radio astronomers sort of based our technique inspired on the optical interferometry of Michelson. Maybe this new technique, which we're using at radio, can be applied to the optical regime. This set off a firestorm, okay? I met Hambre Brown actually in 1998 at a conference in Sicily, so that's a younger me, but that's Hambre Brown. It was quite an honor. And in typical Hambre Brown wit, I would say, he submitted a 1-sentence abstract which said, this talk will give a brief history of the early development of intensity interferometry and its subsequent battle against common sense. And he was right. As soon as this was proposed, he was attacked. He was attacked at conferences. He was attacked by written letters and so forth by people who were realizing or learning about quantum mechanics at the time. Even though treating radio waves strictly as waves was very well accepted, when one started thinking in terms of the optical spectrum visible, we were thinking in terms of photons. And it seemed like Hambre Brown was saying photons were interfering. And in this book by Dirac, in fact, I went to our library, indeed, it says this, when he was describing the 2-slit experiment, for example, each photon interferes only with itself, and interference between 2 photons never occurs. So this was taken, he did not attack Hambre Brown, but everybody else did. He has a Nobel Prize. Hambre Brown didn't even have beyond a bachelor's degree in electrical engineering. Nevertheless, he figured it out that it was a confusion among the physicists. Basically, while there's the existence of a correlation between photons has been denied, it was experimentally proven in the lab by him, and that the error in their assumptions appears to have arisen because of a too literal reliance on the corpuscular picture of light. The reason I'm reading these things here is because this changed my life, this slide. It really did. In practice, the particle picture is more of a hindrance than a help. He was finally backed up. In fact, it didn't even take all that long by other Nobel Prize winners like Purcell, who said the Brown twist effect, as he called it, far from requiring a revision of quantum mechanics, is an instructive illustration of its elementary principles. And I'll say something about in a moment. Hambre Brown said, look, I mean, electromagnetic radiation is electromagnetic radiation. The fact that the correlation should be seen in radio waves, but not seen in optical, really just doesn't make any sense. And the real problem was, the difficulty was, in accepting that the arrival times can be correlated, was that he was talking mostly to particle physicists. That means us, who thought of a photon as a real thing with its own properties like a billiard ball. whereas it's better to think of a photon as an event. That changed my life, actually. If you think about it, that's a real profound statement. A photon is an event, a measurement event or an emission event. Beyond that, there's no photon. Photons don't travel, okay? In fact, if you take that one step further, and it's true, particles don't travel either, okay? I'm serious. But we don't have to talk about that. Waves propagate, and that's the important point. When you measure it, you could talk about photons or not. There is no quantum mechanics in this whatsoever. It's all classical. Keep that away. Okay, with this in hand and with the understanding that visible light as well shows this effect, he realized all he really needs is a lot of light. So he used 2 searchlights from the war to measure the size of Sirius just by separating these searchlights, and he could measure then rather large stars. Now it was time to kind of get going. This was kind of the humble beginnings of quantum optics. In fact, Roy Glauber, who got the Nobel Prize in quantum optics, talked a lot about Hamburger-Brown in his Nobel talk. He referred to this statement by Dirac that each photon interferes only with itself, and interference between photons never occurs. He said, forgive me, this is quantum mechanics scripture, but it's also nonsense. And as our colleague Scott Pratt would say at this point, this statement's not even wrong. It doesn't even compute. So this was a realization based on Hamburger-Brown's work. In fact, this is a slide from Glauber's talk. And really, I would say an appropriate subtitle for the talk, this is why Hamburger-Brown should have also gotten the Nobel Prize, actually. It's much more profound than it seems at the beginning. Okay, this is the observatory that was built finally in Australia. It was a rather large one with large baselines, 2 telescopes that could ride along tracks and be separated. This was used to measure about 40, the size of 40 optical stars and put into a catalog in the 50s and 60s. By the time it got to the early 70s, this had largely run out of gas, largely because of seeing conditions and needing truly bright stars, and also because this technique is not that simple, and Hamburger-Brown himself was getting kind of old. People were moving on into the longer wavelengths, radio, far infrared, Michelson interferometry. So this was the end of stellar intensity interferometry. Okay. One can ask, what are we doing at RIC? Why am I including this in this talk? Kind of how did we get here? So I'd like to explain how intensity interferometry ended up in nuclear and particle physics. We remember I said this was done in 1963 in Australia. Well, in just about the same time, 1960, particle physics was just starting on its own. There was the newly discovered antiproton, and there were studies of the annihilation between an antiproton and a proton at very low energies. In that case, you typically end up with 4 or 6 pions as a final state, okay? As you can imagine, with 4 or 6 pions, you're dominated by momentum conservation. This is a famous experiment done by Goldhaber, Lee, and Pais. And what they decided to do, among other things, is take a look at the opening angle between pairs. So if I have 4 pions, I make 6 pairs. If I have 6 pions, I make, I forget, 15 pairs probably. As I said, you're dominated by momentum conservation. You expect an enhancement back to back just due to this. And in fact, that's what they see. There's more pairs emitted at 180 degrees relative to each other than going into the same direction. Hardly a surprise. What they saw is, well, you know, yeah, that happens both times, but it really looks like the opposite sign pairs act a little different than the same sign pairs. Keeping in mind that quantum mechanics was sort of, by now, well, more or less well understood, at least in the non-relativistic realm. And these are identical particles, pi plus, or pi minus. They said, well, a statistical model, including phase-based constraint, momentum conservation, would predict this. And they said, we think there's something more there. Now, if I had a student come to me with this data and said, oh, I think that I'm going to propose something new that's going to change physics forever, I'd be like, why don't you come back with 10 times the statistics and we'll talk. But nevertheless, they pushed on and said, all right, let's include symmetrization of the wave function in this. And in fact, they ended up certainly with a better fit. And it turned out, with more statistics done by other experiments as well, that this is a real effect. That really the symmetrization of the boson wave function does affect the underlying phase space. And it was seen as kind of a curiosity, like, oh, you know, nice job, you know, symmetrize the wave function. It wasn't a big deal. It was mostly relevant in particle physics in as much as these effects can slightly distort the mass of the W boson at CERN. So if you don't take it into account, you get the wrong mass. Other than that, it was kind of a curiosity, really. Until we get to heavy ion physics. And let me talk about the connection. It was Cherenkov in 1977 who realized that there's actually a deep relationship between the so-called GGLP effect and what was being done by Hambury-Brown. And it's a similar sort of derivation, but here one talks about it in terms of wave functions. I imagine I have a subnuclear source or a subatomic source at the 5 femtometer scale, and I'm going to measure it with detectors at the meter scale. Okay, so this drawing is not to scale. Okay, I can imagine 2 points emitting incoherently within my QGP, let's say, measured at my detector. And so my 2 pions will travel, we could say, as a plane wave. There might be some Coulomb effects, but that's just sort of distraction. Plane wave going from X1 to P1, X2 to P2. And if I write down the wave function for that blue process, I get a creation amplitude for the first particle, creation amplitude for the second particle, and then plane waves as they travel. And one can make that more complicated if you like, but it just distracts from the point. However, these are identical particles, so that process is indistinguishable from the purple process, okay, where I flip the indices. I'm an experimentalist. I don't measure wave functions. I measure probabilities and weights. So of course I have to square the wave function, and I end up with the probability for having one of those particles times the probability for having the second one times something that has a cross term. And this really should not be e to the I, whatever. It should be cosine of the momentum difference times the position difference. So it's not complex, it's real. And now you see the point. I mean, I can measure the probability of making one particle and the second particle, and I can make a correlation function of the 2 particle probability by the product of the single particle probabilities in terms of the relative momentum, and that depends on the relative separation. That's how you measure the size of the source in subatomic collisions. And typically what's done, you plot this correlation as a function of relative momentum, P2 minus P1, and the width of the correlation function tells me the size of the source. Okay? That's femtoscopy in a nutshell. This was developed in the 70s and early 80s by a large cast of people. I would consider these the founding members. There are more than this in the new field of heavy ion collisions. Because, you know, in PP collisions or E plus, E minus, who really cares? The pion wave function is symmetrized, great. But I just told you that with femtoscopy, 2 pion correlations, intensity correlation, you can measure geometry. And geometry is the whole point of heavy ion collisions. That's why we collide heavy ions. We want a big system to be, first of all, a system and to thermalize. So you need to understand the geometry. This is a late measurement, but this is the sort of thing that was being seen. The correlation function of pions, the width of the thing tells me the size of the system. And in the 80s and even early up to 1990, this was the state of the field, at least at relativistic energies. Basically, this was the source determined from HBT or femtoscopy. It was called HBT at the time, versus a to the 1/3. And the nuclear physicists in here know that the radius of a nucleus goes as R naught, 1.2 Fermi, times a to the 1/3. So this is what you trivially expect. This is what you trivially see. It sort of says that the technique seems to work. It's nothing really that interesting to say that I measured the size of a nuclear collision and it's about the size of the nucleus. But one can go further. One can go a lot further. In the past 25 or 30 years, I've devoted most of my career to this. One can use femtoscopy in the systematics to take a look at fast particles and slower particles and pions, for example, and heavier particles like kaons, to explore the substructure of the exploding source, of the hydrodynamic flow. This is the only way to do this. Flow is a correlation between space and momentum. The only way to measure space is with femtoscopy. as a function of momentum. Okay. So one could take a look at a scaling, for example, of this correlation coefficient known as the invariant radius with MT. And this gives us an interior picture of the flow pattern of the exploding quark-gluon plasma. That's also one could do non-identical particle correlations. I won't bother with that, except to say that femtoscopy by itself provides strong evidence for the formation of a bulk system, and it probes the interior structure of the space momentum correlations. It's really the only way to do it, much more than V2, let's say. One can go a lot further than just one-dimensional radii. I won't go into this except to say that if I talk about the relative momentum between two pions, that's a three-dimensional vector. So I can measure sizes in 3 dimensions. They're called Q out, Q side, and Q long. That doesn't matter. But for example, let's say I have a system that's emitting pions, but it's taking a long time. It's heated up, and then it emits a pion, emits a pion, emits a pion. It takes a little while. What is that going to look like? Well, if I measure the particles that go over there, and it's taken a while, out come these pions, and I can measure 2 length scales. The sideward direction, which is about the size of the source, and the outward direction that includes space and time. This is really the only way to get time at the 10 to the minus 24 second scale. Why is that important? Well, we're often thinking about a phase transition where I say, well, if I add energy to a system, maybe the temperature will increase until it hits some sort of phase transition, goes into a new phase, it's once again into a phase transition. This is what we're interested in at RIC, understanding the phases of QCD. And it was a prediction early on before RIC that the difference, or the ratio in this case, between R out and R side, if there was a first order phase transition, as I increased the beam energy would rise and then fall. And the amount of rise and fall was never clear. It could be this big, it could be this big. This took a long time to see, but in the RIC beam energy scan, this was indeed seen. So this is the arc, this is the difference, which is actually a better quantity. It doesn't matter. Basically, how much bigger R out is than R side. You see the difference rise and then fall. And there's even another point out here at the LHC. So this signature was finally seen as a signature of the first order phase transition. The height and the width of it gives us a measure of the latent heat of the transition and the order, in particular, first order. So this is how we can measure, for example, this transition. It's not a critical point. It's actually the transition between the 2 states into a mixed state through femtoscopy.
Mike, can I interrupt you?
I guess so.
So you say, I realize all the literature and stuff. You say it shows it's first order, but there are a lot of other measurements that show that it's not first order, right?
Which ones are you talking about? Actually,
Well, if you, let's put it this way, that's the only one that shows that it's first order.
no.
And no,
The net baryon V1 and the double sign change is very convincing. That was also a prediction which played out.
okay, but okay, let's go to theory then. Lattice QCD doesn't show its first order, right?
Well, talking about that zero baryon number.
Yeah.
Oh, yeah, no, I mean, that's right. That's why we do it in the beam energy scale.
Right, so this is only when you have barochemical potential.
Oh, yeah.
Okay, good.
Oh, yeah, no, we're looking over here. I mean, that's why we're looking around 10 GeV or so.
Right.
So we're looking where the orange is. You're right, it's a crossover here for the
Right.
early universe, definitely. Oh, yeah, for sure. And there are other signatures. I mean, there's the HBT, there's also the net baryon V1 double sign change. And there's at least one more that I'm not thinking of, but they're all soft observables now. I won't say too much more about femtoscopy other than to say when one goes from simple sizes to shapes, you learn a lot. We know that the longitudinal dynamics in a heavy ion collision is different than the transverse dynamics, and one can probe that by looking at the shape of the thing in the transverse and longitudinal direction. We also know that the system evolves and develops, for example, elliptic flow as a function of geometry. And one can measure the size and shape of the source by taking a look at different directions and measuring the correlation strength as a function of angle. This is going to come up later when I talk about Josie's work, exactly a picture like that. and other oscillations as well. I won't go into that. So a lot can be learned from femtoscopy. By now, it's way beyond pions. We talked about kaons, protons, lambdas, anti-cascades, the rest of it. A lot is being done. This is kind of a cottage industry, which I've mostly gotten out of. So far I've talked about stellar intensity interferometry, a little bit about subatomic intensity interferometry, and I want to spend the next hour on modern stellar intensity interferometry. Don't worry, I've already defined the technique in general, and I'll tell you how this works. The point is, the revival of stellar intensity interferometry was driven by the electronics and computing that was largely made available and developed by particle and nuclear physicists. Once again, I go back to this 1954 paper. It's yet another interesting suggestion by Hanbury Brown. He said, in fact, you can extend the baseline as far as you want. It should be possible to eliminate the transmission link altogether and to record the low frequency outputs, he's talking about kilohertz now, of the two receivers to, let's say, magnetic tape. And then the records could be compared later by a correlator so that these stations could be, I don't know, 1,200 miles apart. No need for these cables. Okay, that was an in-principle statement. And he was talking about radio waves with very slow signals. To do it at the optical, you have to really capture the waveform at the gigahertz scale or even higher than this, and then record it, store it, process it later. It was totally out of the question. It didn't even come up as a suggestion, but that's what we're doing today. Okay. So I'll talk about the VERITAS experiment. This is an observatory of 4 12-meter dishes in the Arizona desert. It's made to take a look for high energy cosmic rays. It's been running since 2008, and there's a couple hundred people working on this. So it feels a little bit like a small nuclear physics experiment. It's really been built to measure, as I said, high energy cosmic rays. So maybe even photons or charged particles, who knows? They interact with the atmosphere, cause a particle shower, many of which are charged particles now moving faster than the speed of light in air. And that emits Cherenkov radiation, which is then measured by these telescopes on the ground. So they can triangulate, measure the cone shape and so forth. And looking at the development of the cone tells me, for example, whether it's a proton or a photon. VERITAS has discovered a number of sources on the cosmic sphere, supernovas, black holes, blazar, quasars, as sources of these ultra energetic rays. It's one of the leading observatories for them. However, in order to measure these things, you have to take a look at a dark patch of sky, no light at all. These Cherenkov flashes are extremely, extremely faint. So if the moon is out, you have a problem. Even in the Arizona desert, there's always a little bit of humidity in the air. The moonlight will scatter off of that and make these observations impossible. So the VERITAS telescopes were unused for 10 days per month, let's say. And the question is, well, what do you want to do during the bright moon times? Well, there are 6 of us, that's about all there are in the VERITAS collaboration, who said, oh, we have an idea. Can we use those telescopes? And eventually that VERITAS, yes, sure. What do? We use it as an intensity interferometer. So this is, well, one of the telescopes. Naturally, we don't take data in the daytime, but it's just sort of took this picture. We have light coming from the star, bounces off, of course. This is a spherical meter, not a parabolic meter. So this isn't one you would observe with through an eyepiece. This is used for cosmic rays. We put the light onto a focal plane here, and in that focal plane is a photomultiplier tube, a very small one, as a matter of fact, where we measure the current. Let's see. So all you really see, if it's nighttime and it's pointing at a star, is noise. That really is noise. It's just the intensity of the light having very rapid fluctuations. There's no signal there, nothing like this. Also, it's a parabolic mirror, and you know that photomultiplier tubes just give you current. There's no like, what's the phase of the light? The phase is lost, but you could do intensity interferometry. We store this data locally to rapid disks, okay? And we digitize at about 250 megahertz. So what we have at the end is these 4 telescopes, that is 6 telescope pairs, and I can take a look at the signal from T4 and the signal from T1. We number our telescopes very cleverly. In 2 hours of observation in a night, we're storing about 6.5 terabytes of data, and it is pure noise waveform. However, that noise is correlated. This by a server that I designed and installed, so I'm kind of proud of it. But anyway, this is the correlations that one observes. They are faint, but they are still visible. Let me tell you what we have. Remember I said that the intensity correlations are correlated in time. I expect telescope 1 to see a bright or a dark at the same time as telescope 4 sees a bright or a dark. Not exactly at the same time though. I mean, if the star's over there, then the light is going to hit this telescope first because there's a so-called optical path. That's rather trivial. And as the star moves in the sky, that optical path delay is going to evolve. So as the run goes on, we see that the correlation, for example, moves in relative time due to this optical path delay. That's relatively trivial. You can calculate where the star is with Python tools and so forth. So we know how that should look like. But this is the HBT signal here, evolving in real time as a function of relative time. What we do, like I said, we know where that star is and what the optical path delay is. We shift everything over by a well-defined procedure and we project down onto this axis. This is what we're really looking for. This is the HBT peak. You can see that, first of all, it's very clear with enough observation time and with a bright enough star, basically number of photons, if you like to think of it that way. You can see the correlation is very small. Ideally, in theory, this would be on order unity. However, with our bandwidth, these fluctuations are occurring at the picosecond scale. We're sampling them with 4 nanosecond scale, so everything gets diluted. Not a surprise, but I just thought I'd point it out. Nevertheless, you can find a peak, the amount of the correlation. We take a number of these things for many hours. Josie's data took about 2 years. This is not Josie's data. Each one of these peaks is a point on this graph for a given separation between the telescopes. And you can see we have a reasonable description here. This chi-square actually is a factor of too large for reasons that we know and have corrected since then. Nevertheless, we can measure the size of this star. This is Beta Ursa Major. And I'll tell you something about that in a moment. I will say this is the author list. Most of them are collaborators from VERITAS who had nothing to do with SII. Nevertheless, they're totally welcome as co-authors because they maintain the telescopes and so forth. But I'll point out that 3 of the authors, including the corresponding author of this paper, were OSU undergraduates. Okay, so we have an outsized effect from the undergraduate program. This is the Ursa Major constellation, and it turns out that a number of these stars, not all of these stars, form a moving group, which is to say they're all moving with so-called proper motion towards Sagittarius. They're believed to have formed from a primordial cloud, which itself was moving, and then clumped together. And it's of interest to know, when did that happen? How old are these stars? By using the size of the star that we measured, that I just showed you, and putting this into a complete stellar model that includes all the stellar dynamics, we found that it was about 400 million years ago, which is consistent with previous estimates for the other stars. So it looks like it really is a moving group, and we do have independent measurement of its age. Good. This is a measurement this is another paper that we published on this. This was a sort of a cross-check with Hambury Brown. He measured these 2 stars, which are visible from the northern hemisphere by us and the southern hemisphere by him. Once again, you see the various telescopes pairs in different colors. That's why I like this graph so much. And you can see that they form a common curve, and one can extract the size of the star for Epsilon Orion and also for Beta CMA. It's about a half a milliarc second. This was the first time that digital SII had ever been done, and the first time in more than 30 years that stellar intensity interferometry was done. And they cross-checked very well with the previous measurements. Okay, so we have the 6 telescope pairs as shown here. Now, one thing I want to point out is that when I have a telescope pair, like for example, T1 or T2 and so forth, there's a separation between them, and it's actually the projected separation. As the star goes down, the projected separation between these telescopes is small. If it's directly overhead, the projected separation is the separation. That's why I have many points even for one telescope pair. They don't move. But they also form what's called the UV plane. So if I think of the baseline, the separation between the telescopes, it's really a vector. Okay, so if I consider, well, I actually don't know which ones I'm considering. It looks like T1, T4, and T3, T4. Okay, one might point in one direction and be short, and the other might point in a different direction and be short. So you could consider, what if I measure a round star and I put my telescopes close together and I separate them a little bit and I separate them a little bit. I'll find the correlation goes down and I'll be able to make a plot and tell you what the size is. It's the same if I move them along a diagonal. The question is, can we measure something that's non-round? It's not been done before, ever. Okay. In, for example, an extreme rapid rotator. There's not been sensitivity to this previously. It's been attempted by doing this with the by measuring as a function of angle in the UV plane. Most people thought this couldn't be done even with today's experiment, but Josie really did believe, and every time we went out to take data, she said, take data on gamma Cassiopeia. So we did this from January 2023 to December 2024. It's a long-term project. Got to collect a lot of light. And in fact, it panned out. So I want to talk a little bit about this. I'll point out that this is trivially symmetric because 2 photons is the same as 2 photons. So I'll just take a look at the top half of this graph. And what do I see? This is what we call the pizza plot. I told you that if I take a look at a given angle in the UV plane, I might get one size. Another angle, I may get another size. So what we did is we divided it into 8 slices colored here and fitted each one as if it was a uniform disk, which it's not, but I want to get the scale as a function of angle. It's not obvious to see upon first look, but there is a systematics to this angle, and I can plot this here. So this is now the angular dependence relative to north, east relative to north, of the effective uniform disk size as a function of angle, okay? And we see something on the order of a 6 sigma oscillation, which corresponds to an elliptic bulge, okay? Now, I really like this representation. I made this thing and so forth. It's intuitive to plot it this way, but it's not exactly entirely correct. You really want to, a non-round star is not a whole bunch of uniform disks of different size. It's a nice picture, but that's not really what it is. You really need a holistic treatment of the data, and you ask yourself how to represent the damn thing. I mean, what I showed you before was the correlation coefficient as a function of separation. If I put all these on the same plot, I mean, look, I just told you they're different. So for a given separation, I'm going to have a spread. How do you represent it? I'll tell you, and it's not actually trivial. If I have, here's my UV plane. This is the data points that are, this is the position vectors of the telescope pairs. And we take things, we look at things as a function of our angle. You'll see this in astronomy papers. So I'm going to consider T1, T2, which is red up here, and T1, T3, which is blue. Okay, at our angle -6, when the star is low in the sky, T1, T3 measures a position vector, a baseline vector like this. I don't think we have data here. T1, T2 measures here. When the star goes a little higher, the U and V coordinates change. It goes a little higher, it goes a little higher. That's what these trajectories mean. We take it at different parts of the night, different months of the year. At the zenith, it's hour angle 0, hour angle 2, hour angle 4. Okay? For a given telescope pair, for a given hour angle, there is one visibility that you expect. And that is indeed what we see. This is the visibility now as a function of hour angle for the various telescope pairs. You can see them sort of wobbling around. And the lines correspond to one calculation of a rapid rotator star, including gravitational darkening and all the rest. This is a good fit and a good description of the star. Almost go there yet. The visual representation of the star, this is actually the model that's used. This is in this paper, which is in the publication process right now. It's a so-called Roche-Van Cybele model of the star. It includes rapid rotation, limb darkening, gravitational darkening. I could talk about it if you like to. It also is consistent with spectra that have already been measured. We measure the equatorial diameter. It has about a 40 to 60% bulge, depending if you're measuring via brightness or matter. It's an extreme rotator. It's spinning at 99.7% of critical breakup, which is to say any faster and it would come apart. We can measure the position of the pole angle, which is to say the direction of the angular momentum of this star, also its inclination. And with parallax, we can say what the size in kilometers is and the mass. These are the fundamental things that go into any stellar model. So this is the kind of information that stellar modelers need.
So, Mike,
Yeah.
sorry, simple question. So you can measure the angular momentum position.
Direction, yeah.
Direction, so I assume it's rotating about its semi-major axis or
Yeah.
not?
Yeah, that's right.
Wait, this is 2 dimensions though.
Yes.
It's not rotating this way. Which way is it rotating?
It's,
You're measuring
here's the
this.
axis and it's rotating like this.
Okay.
Yeah.
good.
And to be honest, this is largely what's expected, but because it's identical particle interferometry, it could be spinning this way or it could be spinning that way, but the direction of the angular momentum is the
So, but that's a semi-minor axis, right?
semi-minor axis. That's why it bulges at the
Right.
equator.
Yeah,
That's the equator, yeah. And it has all sorts of features, a gravitational darkening. There's a reason why this side is brighter than that side and so forth. These models are not simple. And they really do need to know the size and the mass. Those are the fundamental features, which you can only get this way.
So is that the first time this has ever been measured?
Gamma Cassiopeia, it has
And it's
been,
rotating and all these parameters?
yes,
You know it's rotating, but okay.
you know it's rotating by spectra, by taking a look at spectral lines and the smearing, the red shift and the blue shift. It has been measured by another collaboration, but only general size, not shape.
Okay,
So they got a general size. I showed you an oscillation of the size. Theirs is somewhere in the middle. So they got a general size. We're getting the shape out of it. As a matter of fact, that's the MAGIC collaboration. Well, that's the MAGIC collaboration, which is in Spain. They recently have released the results on Gamma Cassiopeia consistent with ours.
there are other questions.
And the disc, right? The disc has been measured. It's also how we. know
Yeah,
that
there's
it's-
a so-called decretion disk. I might have mentioned that here. So in the infrared or the near radio, the so-called decretion disk where this star is spitting off material glows. It's not really visible in the visible. We measure the photosphere, but a very extended disk. I believe it might even be Arcmin. It's a very extended disk glows, and it is indeed in this direction. So it's consistent with expectation.
Yeah, so when you say the shape wasn't previously measured, it seemed like the shape was expected from the rotation, like was it measured that it had this shape but not the actual size of the shape, or like?
Let's see. So the orientation, first of all, was expected to be a rapid rotator because you could take a look at the red and blue shifts of the spectral lines. Some parts are coming towards you and some parts are going away. From the decretion disk glow, which had been measured before, one expected the angular momentum to point in this direction. So that wasn't a surprise, which is good because honestly, this is the first time that this has ever been possible to do. And I would be kind of bummed out if the first time it came out to me, what? That's crazy. You know, then it's like I probably screwed it up.
Yeah.
So the fact that it's rotating was known. The orientation was expected to be consistent with the decretion disk. In terms of the details, however, I mean, in terms of, what are the stellar astrophysics that make one part glow towards the poles, whereas you have zero gravity at the equator and you have so-called gravitational darkening, because the brightness goes to the gravitational, to the fourth power. All of these details in these models needed to be constrained by geometric data. Yeah, so it's largely details. Yeah. So I just wanted to mention, this is rather new. These papers that I've been talking about, 2000, 2004, 2005, several of them in 2004, by a number of observatories in Namibia or Namibia, Spain. Also, there's an observatory in France that has some new results, and of course us. And in the future, the Cherenkov Telescope Array, which will have hundreds of these telescopes. They're Cherenkov telescopes. They're not made for SII, but we're going to use them for SII. Hundreds of them separated between the Northern Hemisphere and the Southern Hemisphere, Chile and Canary Islands. So I'll just wrap up, say that this is a rapidly growing field. I mean, really rapidly growing field. These are the papers, the experimental papers. There are lots and lots of theoretical papers now. You get a lot of interest when you finally have data. So right around here, you see the number of papers, at least referenced in the Harvard database, growing rapidly. There's a workshop series that's been started that goes very strong. It's like a strange quark matter for SII. And there's a tremendous amount of instrumentation work being developed for CTA. This is where we were. I showed you this in the late 80s in pion HBT, femtoscopy and heavy ion collisions. Rather sad, okay? I wouldn't call this sad, but this is kind of the state of where we were. This is a publication from 2024. It was largely a demonstration by MAGIC, and it's very nicely done, but it really shows that the size of the stars that they were measuring was consistent with what was expected. But now we've gone further. We're going beyond sizes. And as I told you in heavy ion collisions, that's where things get interesting, and that's where we are now. So I'll summarize. The insight from radar development in World War II led to unconventional techniques and the so-called HBT effect, which gave new insights into quantum mechanics and birth to quantum optics. And let's see, a curious effect right around the time when intensity interferometry in the optical realm was starting to die out, a curious effect in proton-antiproton collisions was observed, and it turned out to be deeply connected to the so-called HBT effect. Once we got to heavy ion collisions, where geometry is crucial, femtoscopy, the measurement of the size and the structure and the shape and the dynamics of the source of the QGP plays a major role, and femtoscopy is the only way to get the spatial substructure. Finally, due to modern advances, largely driven by particle and nuclear physics, we are now able to make a rebirth of stellar intensity interferometry, sort of revive the dream of a much larger baseline. It's a rapidly growing field, and we're moving now finally beyond sizes into shapes. There's the team. It's a kind of a small team, but extremely active team of the people. It's mostly folks from the University of Utah and Ohio State, and our very, very valuable theorist colleague, Jason Offenberg, who helps us understand what the hell's going on.
Thanks, Mike, for this quite interesting.
Oh, you're just in time to
historical
clap if you wanted to.
and interesting talk, Isaac.
Yeah, thanks a lot, Mike. This is probably one of the best talks that combines history and physics that I've seen. I really enjoyed the narrative. I hope you don't mind. I have a question about the second third of the talk, I guess.
Okay.
So as you were explaining the connection between interferometry and femtoscopy measurements in heavy ion collisions, I was thinking the first order difference that I could see between those two systems is that in heavy ion collisions, the QGP is expanding at half the speed of light, basically. So when you get this size, this radius, how do we interpret that? Is that an average radius as it expands?
In femtoscopy?
Yeah.
Yeah, it's a really good question, and it's an important point. So in stars, well, let's talk about femtoscopy. What one generally talks about, this would be, for example, hydrodynamic system. You can as well be a blast wave model. What we find in the blast wave is that particles emitted at this point in space are generally going in that direction. And particles that are going fast generally come from the edge. Particles going slow are coming from a larger region, but if they're going that way, they're generally from that side of the source. These are so-called regions of homogeneity. So if you read femtoscopy papers, you'll often hear about regions of homogeneity. So if I take a look at this plot, these are all coming from the same source, but they're faster and faster pion pairs, that's their MT, and we find that the region of homogeneity shrinks. And the way that it shrinks, if it goes as 1/√mt, which is an approximate scaling, that tells you about the substructure of the flow. Does that help?
Yep, I think so. Thanks.
Can you go to slide 44? I just had a small question on one of the parts of the plot.
Okay.
Also really interesting talk. Just a small thing, why is the E895 plots, they seem to have a much higher slope by comparison to the rest of the trend of data?
The 895 is these crosses. Yeah, that's this is kind of part of the reason this took a long time. One was expecting, and the first quark matter after Rick turned on in quark matter 2001, my postdoc gave the talk on HBT at STAR, and Miklos Galassi, who made that prediction, said, okay, let's see the large R out over R side. And what we saw at the AGS, lower energies, was this light colored data. And what we saw at Rick was this data point, and it looked like it was just flat. It's like, ah, come on, this is terrible. Two things. One is you have to measure the energy dependence. The effect is in between. The second thing is the error bars at the AGS were just outrageous. So in terms of, here's the data point somewhere down here. These are largely consistent with flat. In fact, they're totally consistent with this curve, but they're almost consistent with anything at all. So it's really, yeah, that's my data. That's my publication. It's just how much statistics there are. Measuring one pion at 2 GeV bombarding energy is hard enough. So yeah, you're dying at statistics here.
So you say these like VERITAS telescopes and most of them, I guess, were made to measure this Cherenkov radiation, but you're using it for this stellar interferometry. Like, did you guys go in and install a correlator system and did you make modifications to VERITAS to do these measurements, or was it already prepared to?
It was not prepared, but there wasn't much to do, as a matter of fact. Yeah, we installed a correlator. I installed a correlator, actually. Dave Kita, who sort of, so I told you it was my group and Dave Kita's group at Utah. He is one of these cosmic ray physicists. He was already part of VERITAS. In fact, he was one of the founding members of VERITAS. He was already in the collaboration, convinced the collaboration that this parasitic program wouldn't hurt anybody. And so, yes, we put on a cover plate covering up all the 512 phototubes that are used for Cherenkov observation with a big plate holding one phototube. That's mostly it. Other than that, we reconnect a few lines that go to our disks as opposed to the Cherenkov disks, and it is fairly transparent. But the collaboration was like, we didn't build this multi tens of millions. I actually don't even know how much it cost. Experiment to be screwing around with this new technique. However, they get a lot of new physics out of it. The modifications were relatively minor. And CTA, which is this European project at the $1 billion scale, has yet to accept SII as an official data, as an official science goal. They have all these layers. I mean, it's European after all. They have scientific working groups. I am the scientific coordinator for SII, and we are trying to convince them that, again, we're not going to hurt anything. This is added stuff for no cost or very low cost. Yeah.
But there's a lot. I mean, there are a lot of detectors, right?
Yeah.
So.
But you don't have to instrument them all.
Okay.
Just instrument, some.
Yeah, very excellent talk. I guess my question is, what is particularly interesting to point this at next? Like, you've seen the rotator, you kind of knew that would be interesting ahead of time. Are there any other specific things that you are dying to potentially resolve, or would you just point at stuff until you see something interesting?
I think right now, a lot of it is still in the proof of principle stage. However, one thing that we're interested in now is imaging a binary system. So in particular, Spike or Alpha Virginis. So that's a binary system where the size of the orbit is about 10 times the size of the star. That means they're interacting, even exchanging mass sometimes when they come close. And you'd like to see this thing evolve with time. There are some predictions about what the ellipticity of this system is and the general geometric features. And that's what we're working on very actively now. That will be our next paper, I'm fairly confident. So that if we can image a dynamic system then that really passes the next stage. We'd also like to, if Aurora Borealis ever goes off, we would like to image this thing in the early stages. That means in the early hours. Got to get down there and watch this thing evolve. After a few hours, it gets so large that we're not able to measure it. It's also much less interesting after a few hours. So that's one thing we'd like to do too.
Oh, awesome.
So do you have the data already for the binary system?
Yeah.
Cool.
I can even show it to you. It's really cool.
Okay.
Are you part of like I guess a snooze or stuff like that where so that's like the collaboration.
Alert
Yeah,
system.
for supernovas,
Yeah, we're part of snooze. I wish you could snooze. I mean, you're on shift and it's like 3 a.m. and it's like the data acquisition's going fine and then it's like, and it's Jesus Christ. You know, and it's great when you're doing Cherenkov observations, but when I'm there, we're not. So I try to turn it all the way down,
See.
but yes,
Okay,
VERITAS is definitely part of that. And as soon as you hear one of these things, then there's a recording and you're supposed to aim your telescope.
Right.
But
I
we're
see.
not doing
Okay, so it wouldn't help, okay, I see.
that. Not when the moon's out yet.
Okay.
Okay, Mike, thanks for this very nice talk.